Thank you, Scott and Edu, for the invitation, everybody, and the nice introduction. I'm really honored to be here. Can everybody in the back hear me? Awesome. I'm really honored to be here, and I'm currently a faculty at the University of California in Merced. And because we're a new campus and most people are not really sure where we are, I just wanted to start by giving you a visual. We're the UC campus that's closest to Yosemite. So the prettiest place. But today I'll talk to you about some work that we've been doing since the time I was a PhD student at Berkeley and continuing. Yeah, so I'll move on, but without I go any further, I really want to acknowledge this work started as my PhD research, but it continued as research for my graduate students and postdoc. And so a lot of the data that I'm talking about today, credit goes to them, and so I want to acknowledge them, a lot of collaborators and funding that has continued to fund this work until recently, until now. Okay. So I'm a soil scientist. I really care about how soils are developed, how soils are distributed across the Earth system. And I think I wanted to start with these two kind of pieces of ideas and motivation for why I study the things that I do. One, I really feel like relief is an important component of soil development and biogeochemistry, and I'm so really interested in understanding that piece, and today's talk kind of fits into that. And then I'm interested in trying to think about how relief interacts with climate in many ways to affect carbon sequestration and several other variables. And as I give this talk, I want to also emphasize the fact that the topic I'm discussing, soil degradation in particular and erosion processes, are really vital. And the soil resource around the globe right now, a big portion of it at least, is facing existential threat from from all sorts of degradation processes. And I think this has now become a much bigger societal issues, where if we are going to think about not just the climate implications, but also the food production and other related variables, we really need to think about the soil security part of this idea and thinking about how our security is intricately linked to the health of the soil system and how we manage it and understand it. And then kind of zooming in a little further, a lot of my work deals with soil organic matter, though. The dead remains of plants and animals and microbes that used to live in soil and their processing, and they're byproducts of the processes of organic matter. And I think, as many of you would be aware, soil organic matter is a really integral part of soil, typically not more than 5% or so by mass, unless we're talking about organic soils, but it influences several key processes in soil, including the biota, the chemistry, and the physical conditions in soil. And then, as many people have attested, I think historically, a lot of the structural complexity and the complexity of the soil that we attribute is actually a result of the structural complexity and dynamics of soil organic matter. So I feel like these are two great motivations to kind of think about the topics that I'm going to take you through today. Okay, so the main message of my talk basically is going to be to convince you that erosion exerts a very significant control on distribution and stocks and persistence of carbon, how long it stays in the soil system as opposed to get mineralized and go back into the atmosphere, and that this has important implications for our climate. And this is also something that the Earth has developed, the Earth system has developed to it, but something that's changing quite a bit with anthropogenic erosion. So I'm going to try and convince you that erosion plays a major role in terrestrial carbon sequestration and hence the maintenance of our climate system. And so to do that, I'll start with a little bit of background on both carbon sequestration and erosion, just to kind of, we're all on the same page about how I'm thinking about this, and then move on to what we named the erosion-induced terrestrial carbon dioxide sink, and think about how erosion affects persistence of carbon and fate of carbon that's eroded from soil. Okay. So the term here, carbon sequestration, obviously is referring to these combination of processes that lead to removal of CO2 from the atmosphere and its storage in a reservoir in the Earth system. In our case, we're thinking about the land reservoir, in particular carbon sequestration in soil. And when I think about carbon sequestration in soil, then you can easily visualize it from this kind of perspective where the amount of carbon we have in any kind of soil is a function of the input and output of carbon. And the dominant inputs that we recognize are from plant productivity and deposition of matter that was carried by wind or water. And then the dominant outputs being respiration or decomposition, and then erosion and leaching of that carbon. Then carbon sequestration in this formulation is simply then when it happens when carbon uptake on overall is bigger than the carbon release back into the atmosphere. And when you think about where we are currently with our climate system, you can think of the fact that there is now, somewhere on the order of about 8 petagrams of carbon or so that is continually being released into the atmosphere because of burning fossil fuel. Another one petagram carbon or so because of land use change. But then think back to how much our atmospheric CO2 concentration is increasing, though. That's typically on the order of about 4 gigatons or 4 petagrams per year, which is about half of this, right? So the rest of the half is being captured by the land sink, which is a combination of sink in the growing biomass as well as soil, and then the other half going into the ocean. And I'm going to show you next then that we actually know quite a bit and can predict very well the ocean sink, and it varies relatively small. But the land sink is very variable. And the amount of carbon that's captured in the land sink seems to change depending on human activities overall, but also as a function of climate. Hence, there's a lot more uncertainty associated with the land sink as there is with the ocean sink. Okay. And then the second topic that I'm relating these to, though, is the process of soil erosion, which is simply the lateral movement of topsoil on the Earth's system, right? And this could be because of water, wind, or even gravity-driven diffusive mass transport. And obviously, since the beginning of time, there was soil erosion. As soon as there was any kind of slope, and there was soil on the surface, you can imagine that it will move downhill because of any number of these variables or combination thereof. But this is typically a very slow process, right? And the rate of soil formation is at the very least matched with the rate of soil erosion. Hence, it doesn't affect how much carbon is in the soil at any given time, if we think about it, or long-term perspective. But then we're now dealing with accelerated rate of erosion that is simply caused by human activities, and that we recognize as, especially in the last couple of hundred years or so, the rates picking up considerably higher than the background geologic rates of erosion. And in many cases then, the rate of soil erosion can even be faster than the rate of soil formation, hence continuously leading to net loss of soil from any kind of eroded landscape. It's also important to recognize that this has a huge economic cost, right? By some estimates, erosion in ag lands, which is mostly driven by water erosion, costs us about $400 billion or so in terms of just the economy cost and lost productivity. Hence, a really important variable to consider. And the other way to think about this is also the fact that the rate at which human accelerated erosion is happening is responding to climate change in multiple ways, especially when you have drought and devegetation or loss of vegetation that protects the soil from erosion. And the flip side of climate change, you also have intensified hydrologic cycles. So both of these seem to be helping increase the rate of erosion quite significantly. And at this point, we're probably reaching or approaching ability of the soil to recover from degradation. Hence, it's a really important concern. I'm not necessarily going to talk about these concerns, but I just wanted to make sure that we're all on the same page. I'm not ignoring the fact that there is accelerated erosion. But for the purposes of most of this talk, we'll talk about geologic and natural rates of erosion, but bring in this a couple of times. Okay. So as I said, erosion is just part of how the world works, partly because the world's not flat, right? I know it's convenient for some of the studies that we do to assume that anything we do, experiments and results we get from flat landscapes can easily be extrapolated to the Earth system. But obviously, that's not easily doable. If you look at the world on a 1 degree by 1 degree scale, about 64% of the land area has slope greater than 8%. And these are pictures I captured from my flight trying to land in Salt Lake yesterday. So nobody here disagrees with me, right? You're all very aware of how this is all supposed to work. But what that means is that erosion happens for all sorts of reasons, all the time, right? Soil moves, and sometimes it moves because of the wind and water kind of variables that I mentioned. Sometimes it's because burrowing mammals, for example, take out soil, put it on the soil surface, and it just moves downhill because of gravity-driven processes. Or in many cases, we increase the rate of erosion so much higher, as we said, through all sorts of human activities. So then if I take you back to how we started, right? So erosion has a factor and plays a really important role in how much carbon is in soil. But in the long term, it also dictates the slope of the landscape, right? What used to be topsoil material from hill slopes eventually moves, and most of it is accumulated in depositional settings. Hence, it changed the slope of the landscape. It redistributes and remixes soil along the way. And then I think there's been ample studies that have documented that erosion changes the input term in the equation that I showed you earlier for carbon dynamics, because it affects plant productivity, it affects even distribution and type of vegetation, but it also changes decomposition rates, leaching rates, and even the export or removal from that catchment of sediments. So if we really want to understand how much carbon is in soil and where it is and be able to extrapolate to a larger scale, then we really have to think about how erosion is redistributing topsoil material and what's happening to the carbon from this kind of perspective. Okay, so just to give you a couple of numbers that are significant in this case. So right now, at least some assessments that have been done fairly recently, we know that somewhere on the order of about 1.1 billion hectares of land is affected by soil erosion, where at least there is significant erosion happening. And that means that roughly about 75 gigatons of soil is moved around on an annual time scale. And then depending on how much carbon on average you think there is on topsoil, that number translates to somewhere between 1 to 5 gigatons of carbon that is moved around. Another very, very important variable to remember when we talk about this, though, is that 70% of that topsoil material that is moved from hill slopes never makes it out of the original catchments that it was eroded from. By some estimates, that number is actually closer to 90%. So 70 to 90% of the mass that was transported from hill slopes is simply moved downhill and deposited in floodplains, foot slopes, or even reservoirs, lakes, and things like that that are downhill or downstream. So then, if we recognize these variables, then we have to recognize that in this global area that's dominated by dynamic landscapes where matter is being moved around, then the biogeochemical cycle of any element that we want to look at is going to be affected by not just the ecological soil and other related variables, but also by the geomorphology of the landscape. So the big objectives that guide our work in this field is, one was motivated by trying to resolve uncertainty around how and to what extent carbon sequestration is affected by erosion. And then we wanted to understand, how does then this affect stability of carbon in the soil system? So if soil is being moved on topsoil, does that affect its long-term fate and how long it's likely to stay in soil in reduced forms as opposed to oxidize and go back into the atmosphere as CO2? And so we think this is a really important variable to think about, because soil erosion is the only mechanism that we know of, otherwise stable carbon, that is either bound to mineral surfaces or is inside aggregates, so either physically or chemically stabilized against decomposition. That's the only way of how we know that this otherwise stabilized carbon can be moved around, right? But when wind moves, we also know that the environment under which decomposition is happening is changing. So we think it has a really important implications for fate of carbon, as I'm going to show you in a minute. So I'll be upfront and start that this is not necessarily a topic that's settled in the literature. It's getting there, but it's not necessarily a topic that's settled. This was from a synthesis that we published last year, basically showing where the estimates are in terms of whether erosion induces a net sink for atmospheric carbon dioxide, everybody on this side, or whether erosion induces a source term, meaning does the disturbance of soil by erosion, the physical mixing, breaking down of aggregates, does that lead to net carbon loss into the soil or net carbon storage in soil? I firmly rest in this camp, and I think a lot of people have done a lot of work to show that, at least from a mechanistic standpoint, the sink might not be huge relative to the soil carbon storage potential, but at least it seems a positive number. And I want to also acknowledge that I won't go into detail that part of the reason why we reach these contradicting conclusions is because we come at it from very different perspectives. And that a lot of the work that was done to prove that erosion has to be a source was really done at a plot scale in agronomic kind of settings. It doesn't really take into consideration the very types of landscapes and biomes where erosion actually takes place. And that's easier to explain, for example, that in this kind of formulation, right? If I'm looking at this plot and I do all the calculations to figure out how much carbon is in soil, how much is coming in because of plant production, how much is going out because of decomposition, and then I factor in how much is moving because of erosion, eventually I will get to a net source term, right? Eventually I will get to a point where the amount of carbon that's in this place after erosion is going to be smaller than the carbon that I would have had without erosion, right? But that's only if I stick to that perspective. If I remember what I just told you, that 70% of that carbon that's moved from here is eventually lands in a depositional setting like this, where yes, there might be higher rates of erosion, but there's also higher rate of protection and even increased rate of carbon input because of higher NPP in depositional settings, then not so much. And I'm going to go into detail and explain this in a minute. And this is what I mean with persistence, too. So when we think about soil organic matter persistence in my world of organic matter biogeochemistry, at this point we recognize that the carbon coming into the soil can stay in soil and be stabilized if it is physically isolated from decomposers or water, or it forms some kind of chemical association with soil minerals. So it's either sorbed onto the surfaces of the minerals, or perhaps even inside aggregates, or some kind of climatic condition is kind of making decomposition very difficult. So that basically means that we're thinking a lot of the decision or the consequence of whether soil is going to be eroded, decomposed afterwards or not, rests on where that carbon is decomposing, under what environmental conditions. And you can imagine then that erosion plays multiple roles in whether carbon is isolated or not, or whether carbon can form stabilizing associations with soil minerals. Let me explain what I mean here. So when raindrops fall into a soil and the kinetic energy hits the particles or the aggregates, yes, it's going to break them apart, right? It's going to break them apart though, and then they are washed down and deposited downhill with a range of the clay particles and other things that are now decomposing together in that kind of setting. And if the erosion or the depositional position then has different hydrology, different mineralogy, different even biological inputs, that will have an effect on whether the carbon is now physically isolated from the forces of decomposition or not. The other way to think about it is that if topsoil is being eroded, it's not just carbon that's being eroded. Some finer particles that are also in the topsoil are being moved around. Hence, if you move both carbon and these fine particles, which tend to be very reactive, they actually eventually, at least in some, might have an effect on stabilizing the carbon because they will promote aggregate formation. They also seem to be promoting chemical association of the carbon with soil minerals. And I'm going to show you a couple of data points to highlight what I mean by this. But I want to start with the first point that we discussed. So, okay. So I mentioned that, at any given point, then the amount of carbon you have is a function of NPP and respiration. You can also think of the fact that the thickness of soil at any point in a hill slope is a function of the rate of soil production from bedrock and erosion. And then when you think about carbon sequestration or dynamics in an eroding system like this, you have to take into consideration how much carbon is coming in and out of the soil through these mechanisms, how much carbon is being relocated, potentially how much carbon might be, kind of decomposing during transport. And then once, most of the carbon is at least deposited here, then how much does that contribute to change in the rate of respiration or at least the rate of stabilization in soil? And a lot of the work that we do, and several of the people that are on the green side of that figure that I showed you do, is about trying to calculate watershed carbon balance. Take into account how these different opposing fluxes are being affected because of erosion, and take into consideration conditions before erosion or after, and to arrive at a watershed level carbon balance. And in this case, then, if we end up with a positive balance, obviously means erosion is inducing a carbon sink. The opposite if it's a source. And one of the ways that we've done this is basically to modify a very popular, very simple first-order kinetic model of carbon sequestration, which basically says what I showed you earlier. The change in carbon in a soil over time is a function of input and the rate at which the carbon pool is decomposing. Yenny's formulation of the model basically attributes this loss to oxidative decay. What we've done basically is just add another K term here to account for the fact that the net loss or change in carbon that you have is a function of not just oxidative decay, but also how much is being moved by erosion. But this KE term can be obviously positive if you're losing carbon by erosion, but negative if you're actually considering this plot in the landscape where erosion is all of a sudden now a gain term, right? Because erosion's bringing in carbon to the depositional settings, but it's taking away carbon. So it's an added loss term here, but it's a positive term that's adding to the pool in the depositional setting. So that allows us then to take into account these loss variables by decomposition and erosion. And then we also account for the how plant productivity or the net input of carbon into the soil pool is changing in the eroding versus depositional settings, and taking into account how much area is covered by eroding versus depositional settings. We can then set this criteria that states that if post-erosion carbon stock, after you account for all these things, is positive, then you're going to end up with a sink. Or you can simply state the criterion for whether erosion constitutes a sink or term by saying that for erosion to constitute a net sink for atmospheric carbon dioxide, one, at least some of the carbon that's being eroded and moved away from hill slopes has to be replaced by production of new photosynthate. So that soil can't be completely eroded and stripped away from all the soil that it can't produce any more plants or it can't store any more carbon. And then you also have to state that at least some of that carbon that's eroded from the hill slopes has to be stabilized in the depositional settings. So if you fulfill these two things, then it's very easy, then becomes easier to see why erosion constitutes a net sink. Those of you who have followed me this far would also realize that these things mean that this criteria allow for one of the above conditions to be violated as long as the other one is strongly observed, right? So if you end up with rate of plant productivity after erosion that's considerably higher than what you started out with, you can still make up the erosional loss. Or if the rate of decomposition of that eroded carbon is considerably slower considered to where you started out with, you can still end up with a positive sink term. And as long as the process of soil erosion is leading to more carbon being removed to the atmosphere than is more removed from the atmosphere than is being released, then you still can get a sink term. And we've gone to many, many places and people who work in this to test these ideas and these criteria. And so here, what you're seeing is the rates of soil erosion across the US, and each dot here equals to about 40,000 kilograms of soil loss per year for erosion. And we picked a couple of sites here in Mississippi that is cultivated, highly eroding site that has anthropogenic influence, and then picked another site in Tennessee Valley. This is an undisturbed grassland that has not even been grazed, at least in the 20th century, if not even 19th century. But it's a long-term kind of land that is in a long-term preserve, where we know that there is no anthropogenically accelerated erosion, at least not for a long time. And the main reason why erosion happens in this site is because there's an active community of pocket gophers that borrow soil, bring it out to the surface, and then it moves downhill because of diffusive transport. So as you can imagine, very slow natural rates of erosion, highly degraded system that is seeing considerably heights of erosion. So I'm just going to compare some of the results that we've had from these two sites to show you how this should work out. So both these soils have similar, relatively speaking, soils, but and climatic settings. But as I mentioned, the Tennessee Valley sites hasn't been disturbed. The Mississippi is very highly disturbed. And if you think about how much carbon is in topsoil, in the undisturbed natural grassland in California, it's a very high, relatively speaking, carbon of about 2.2% relative to the 0.7% in Tennessee. The rate of erosion is also dramatically different, an order of magnitude at least higher in Tennessee. But both these sites also have roughly about the same amount of the carbon that is eroded from the hill slopes that's actually deposited in a depositional setting downhill. And I should state here that you might be wondering, how is it that this soil gets eroded this much every year and it still is productive? It's the magic of fertilizers and irrigation, right? So this site is highly managed, and they keep adding fertilizers and irrigation water, so it still continues to produce soil, to produce a lot of carbon, relatively speaking, and that's coming to soil. So then you can think about the net primary productivity in both sites, which are now comparable because this is supplemented, but this is not. But if you think about what proportion of the carbon that is that's produced by plants is actually stabilized every year in the soil, contributing to buildup of the soil carbon pool, then relatively speaking, it's very little in Tennessee Valley, the undisturbed California site that already had a lot of carbon, right? But it is considerably higher in the Tennessee Valley site. The other way you can think about this is that of all the carbon that is produced by net primary productivity, something like 90% or so goes into, is quickly decomposed, so it doesn't really contribute to the soil pool. But this is really typical of most natural systems. About 70%, which is also fairly typical of ag systems, goes into maintenance of the soil carbon pool. But then you still end up, though, with a much higher carbon stabilization potential in the eroded, highly degraded site that doesn't have much carbon than the one that actually has a lot of carbon. And this has to do with the fact that this soil is so far removed from its soil carbon saturation point that it has so much potential. As long as carbon is coming to the soil, it has potential to stabilize it. Does that make sense? So then, kind of a considerable amount of carbon is coming into the soil to keep the carbon pool, to maintain the carbon pool in that soil. So both of these sites then constitute a positive sink term for as far as erosion is concerned. And I want to kind of highlight this one point to make sure we're all kind of convinced about this. Because if you think about the criterion that I laid out early on, the only way that carbon would not be stabilized, would not enter the soil pool after erosion, even in Tennessee Valley, is if the fraction of eroded carbon arriving at depositional settings is zero, meaning everything is completely washed away from that catchment and nothing stays within that hill slope. Or if as soon as it's delivered to the depositional setting, all of it is quickly degraded and it doesn't contribute to build up of the soil carbon pool. And neither one of these conditions is actually realistic, under most erosion conditions at least. Hence, you end up with a net positive sink term in both cases. And as I mentioned, the higher theoretical, at least, potential to stabilize carbon in a degraded system has been discussed quite a bit in the literature as the soils that start from lower percent carbon or lower carbon saturation being able to quickly accumulate carbon or build up and replace the lost carbon relatively quickly than soils that start with a higher carbon saturation. Okay, and I think it's important at this point to also remind you that we wanted to make sure this had implication for not just natural erosion, but also anthropogenically accelerated erosion, because as this kind of data and then projections looking forward indicate, erosion is likely to only get higher, right? But at the same time, the reason why I keep kind of focusing on why does deposition of that eroded carbon downslope matter is because we've also, because of human activities, increased the amount of area that's available for storage of eroded carbon. What this figure shows you is from a paper that Bob Stella, the USGS scientist, published in 1998 on this topic, is where he basically went out and dug all sorts of data that's available on the area that's covered by different types of landscapes, and especially areas that could be considered depositional settings for eroded carbon. And part of this work was motivated by the fact that geomorphologists had been documenting increased rate of erosion because of human activities, but there wasn't higher rates of sediments being eroded that were reaching the ocean. So it was clear that a lot of the sediment was staying on land somewhere. And so they wanted to figure out where in the land surface it was going. And this is the bars are showing you that the dark is pre-industrial size of the area that was covered by these types of depositional settings, pre-industrial period, and then what is actually happening during the industrial era. As you can see, there's multiple types of settings that have changed quite drastically. And that amounts to the increase in depositional area that is equal to somewhere about 3.5 billion meters squares, with the potential to store somewhere in the order of 4.4 gigatons of carbon per year. So I don't want you to think that that's all the carbon that is kind of contributing to carbon sequestration, because some decomposition is going to happen during transport and also during transport, and even after the carbon's deposited in a depositional setting, it's going to go through decomposition. So that might not necessarily be all of this, but even if it's half of it, it's a huge number, right? If you remember the numbers from the global carbon cycle. But I'll take you through this to remind you. So this is proportional to basically the sizes of these are proportional to the numbers that are there. These are the fluxes that are we releasing. And this data is not slightly different than the one I showed you earlier, because this was calculations that were done at the time this paper was published. And I wanted to show you that. But they're very similar though. So somewhere close to 9 gigatons being released to the atmosphere only increasing 4.2, because some of it is going to oceans and some of it is going to land. But this combination that we thought was going to land was, as I mentioned, was uncertain, right? We were pretty clear that the land was taking up at this point about 0.8 gigatons of carbon per year. But this 1.1, which was the difference between the ocean, if you sum up the ocean and the land sink, and then the increase in the atmosphere, the difference adds up to somewhere in the order of about, somewhere on the order of about 2.2 or so. Oops, that number should be like this. Which is basically that if we do our calculations and arrive at 1.1 or 1.2 gigatons of carbon sink for the erosion-induced sink, that becomes about 2/3 of this missing sink or terrestrial residual sink that we couldn't quite figure out where it was going, right? So it becomes a very significant number. In fact, when we go back to this calculations and try to be as conservative as we possibly can in thinking about what proportion of that 4.4 gigaton carbon is likely to be stored in the long term, we come up with numbers that are on the order of about 0.7 gigatons of carbon per year. But that's still a very significant number, because that additional carbon storage on land because of soil erosion is equivalent to, considering values at that time, 10% of the fossil fuel CO2 release. So that's all additional, we're talking about carbon storage, that is only attributed to this one process that is likely having a significant influence. Okay. And then I mentioned that I also wanted to think about persistence of carbon. And the persistence of soil organic matter, as I mentioned, is a function of the environmental conditions that it experiences, be it change in the physical condition or the chemistry or in the environment, potential for sorption and desorption. And another thing that I mentioned earlier is that when topsoil is eroded, it's not just carbon that's there. Soil minerals are there too, right? And in fact, we know that the fine soil particles, the clay-sized particles, and even smaller, more metal oxides and such that are smaller, they are preferentially eroded during water erosion in particular. And they're even preferentially deposited further down so that in depositional environments and not just moved a little bit from their source area. Hence, having carbon being eroded at the same time with reactive minerals, we hypothesize has to have a huge implication on its stability. And the first evidence that we've done here is, here I'm showing you from two different types of eroding positions and two different types of depositional settings in the same hill slope in the California site that I mentioned earlier. You could see first the carbon inventories. So there is somewhere between 2 to 3 times more carbon in depositional settings than there is in the eroding slope positions. Part of that is attributed to the fact that soils at the depositional basins are simply thicker. There's a lot more soil depth to work with. But then if you do a radiocarbon analysis, which tells us about how fast the carbon is cycling, and in this particular calculation, I'm also presenting the weighed fraction modern, which basically weighs the radiocarbon concentration by the amount of carbon that you have. And this allows me then to ask questions of, is this soil just accumulating a lot of new carbon? Hence, it's not stabilizing carbon, but is it actually accumulating a lot of old carbon? Hence, it must be playing a major role in stabilization. And how it works is, if the number is closest to 1, then it means it's not as stabilizing, relatively speaking, compared to if the number is actually smaller. So this ratio would go from 0 to 1. So what we have here is, if I compare, these are sites from the same hill slope, very short hill slope. Relatively speaking, there's about 200 meters horizontal distance here. So it's a very small hill slope, but just simply based on the geomorphic setting and the slope of the landscape and curvature, I get considerably higher, especially in these higher positions of this weighed fraction modern value than I get in the down here. So what it's telling me is that in these depositional settings, there's not just a lot of carbon being accumulated, but there's also a lot of old carbon. Hence, they're actually stabilizing carbon. And part of the clue then you can think about by what's happening and in what kind of setting will give you an idea of the stabilization potential. And we think about carbon, in soil as being composed of a pool that's dissolvable, a pool of carbon that is freely floating around in the soil that is not protected in any way. These are my representations of soil minerals. I'm not a good artist, but they do the job, right? But it could also be stabilized either by being inside aggregates, where the diffusion of water, energy, and water extracellular enzymes is limited, and also microbes can't access it, or it could be chemically bound to the surfaces of minerals. And I mentioned that erosion is the only way that we know of, especially this pool of carbon, which constitutes a huge proportion of the soil carbon in soil, can actually be translocated in large quantities. By most accounts, most carbon, over 3/4 of carbon in soil is in this pool. And hence, if there is a lot of potential to stabilize carbon, which would be attributed to especially reactive minerals that provide a lot of sorptive surface for stabilization of carbon, then you would expect that a lot of carbon would be not just stored, but also stabilized in these depositional settings. And in fact, we looked at those reactive minerals. We did a whole host of chemical selective extraction procedures that I won't go into detail, but to give us an idea of how the concentration of crystalline iron minerals, poorly crystalline short-range order minerals bearing iron and aluminum, and even the pool of carbon that is chemically bound to iron and aluminum, and how that changed as I move through this landscape from eroding to depositional settings. And what we find in all cases is that the eroding positions, the two down here, have considerably smaller concentration of reactive minerals than the reactive minerals that I see in the depositional environments. So the potential is there to stabilize carbon. So this movement of soil particles on the soil surface along with carbon provides not just for carbon storage a different place in the landscape, but also its long-term stabilization in this pool. Okay. And so the next kind of set of projects, which are fairly new, have been trying to get us to think about, so how does this all play out in forested ecosystems, which are a little different, obviously, right? Like grasslands or ag lands. Because in forested landscapes, you have a lot of carbon in the form of litter and free particulate matter that's sitting around on the surface. And if you're from the Sierras or even here in Utah, you see that a lot of the forests also are in fairly steep landscapes where erosion is a very dominant process. So we went into that as part of the Southern Sierra Critical Zone Observatory in California, and we're starting to think about what does this mean for long-term implication of the fate of the eroded carbon. So I'm going to go back to the same figure that I showed you here. So we're trying to figure out if any of these pools of carbon are selectively mobilized when we think about a forested landscape. And I care about if any of these pools are selectively mobilized, because if I think about what's right on the top of the soil surface, as I mentioned earlier, there's a lot of particulate carbon that's not necessarily stabilized by association with minerals. There's also a lot of carbon, just simply higher concentration, higher carbon to nitrogen ratios, and the carbon here is more derived from plants relative to if I just consider deeper in the soil profile, right? Deeper in the soil profile, I'm more likely to find carbon that is more processed, more microbially derived than plant-derived, and it's also older, it's been there longer, it has formed association with minerals. So if you go back to those pools that I showed you, the free and water extractable pools or dissolvable are likely to be enriched on top of the soil surface, while the mineral-associated pools, both physical and chemical, and some water extractable, is likely to be found at depth. And then this has implications for what is eroded from this forest hill system, right? Because if I'm considering surface overland flow under fairly low precipitation conditions, most of the carbon that's eroded is probably going to come from here. But if I'm considering subsurface base flow processes or events that come because of high precipitation, which is likely to be less selective for the light particles, but more mobilized, just a lot of everything, then more of this protected pools of carbon are likely to be eroded. So we started with the process then as part of the Southern Sierra. We worked at 8 catchments, 4 at high elevation and 4 at lower elevation, because this allows us to control for the type of precipitation, the low elevation being dominantly rain and the high elevation snow, so the hydrology and the water flow through the soil being different. And so we selected transects across all of these catchments where we sampled at geomorphically distinct positions of a crest, steep positions in the back slope. We captured a depositional toe slope position, but these catchments, thanks to a lot of work by Forest Service, were also instrumented, and they had sediment basins at the bottom. What that means is every year, all the material that's eroded from this catchment is caught in these sediment basins. Overwhelming majority of it, at least. Something in the order of like 97% is the capture efficiency that they estimate. So what that means is at the end of the year, then in August, we can go in, they go and determine how much mass was mobilized, and so we take subsamples and figure out where does that carbon come from or which pool. And then the data here is showing you by plot for 15N concentration on this side and the 13C. And these isotopes of carbon, without going into much detail, tell you, so the 13C is going to tell us about the source of the carbon, what kind of plant was it derived from. And 15N is a very good indicator of how processed the carbon is. So the more processed or decomposed carbon is, meaning if it's in deep soil, the kind of should show up on the right side of these figures. And the numbers here are not too huge in terms of difference at 13C. These are all derived from generally the same type of C3 types of plants. With perhaps a little bit enrichment that is attributed to decomposition. But I think the interesting story is in the spread of the 15N values. That you see that when we consider the soils that were sampled at those different landscape positions, the mineral soil samples, as well as the forest floor material that was captured from each of these sites. And then we compare it with sediment that was captured at the basins at 5 different years. We notice that all the blue dots show up somewhere in there, right, in the mix, but a lot closer to the green, which is the forest floor material. That under all these climatic, very variable climate conditions, there's some variability that we can attribute to climate variability, but overall, we can say that with confidence that pretty much most of the carbon, especially in the high elevation sites that's coming, is actually coming from forest floor material that's being eroded on a yearly time scale. And then we go a little bit one step further, and we try to separate those pools of carbon that I mentioned. Remember, the unprotected pool, the physically protected pool, and the chemically protected pool, because we want to go beyond saying just what's the bulk soil organic matter signature into thinking about how are mechanistically these different pools potentially moving at different rates in the landscape. And this is a fractionation scheme that my former postdoc and I worked on. But the main message here is that if I focus on the pool of carbon that is in the free organic particles or in the water extractable pool, our data tell us that in both these 2 years that I'm plotting here, which were 9 was relatively dry and 10 was relatively wetter years, we noticed that in both years there is a selective transport of that light carbonaceous material, the particulate matter that's on top. That's probably less surprising, right? You would expect that if it's on the surface, it should get eroded too under most conditions. But then what we notice is that the water extractable pool, the carbon that's most bioavailable, easily decomposable pool of carbon, is selectively being mobilized in years that are wet compared to years that are dry. That also kind of makes sense. The other thing that was really interesting to me, though, is that there is selective transport of carbon that is bound to mineral surfaces. So otherwise stabilized carbon in wet years. Remember, as I said, if there's a lot of water, it's just there's a lot more energy to take a lot of things downhill with it. Hence, we see evidence in here that indeed that otherwise stabilized pool of carbon is actually mobilized quite significantly under wet years in these forest ecosystems. And we even show that this is also reflected in the radiocarbon signature of the carbon that is eroded. This is the carbon that is in these forests compared to grasslands and croplands that myself and others have worked on. And what I think this alludes to is that it's telling us that in these forest ecosystems, things can get a little complicated in terms of the carbon sequestration potential, because the pool that's being mobilized is so easily decomposable that it's full of this particulate matter and dissolved water extractable pool that unless this material is stabilized further down in these catchments, it could potentially be lost and because of this mobilization. And I'll skip that to just kind of, was a summarizing, I'm assuming we're getting close. No? Okay, I'll go through it then. So the synthesis of this is that when soil is moved on the landscape, it has multiple implications for carbon dynamics because, one, it affects the rate of decomposition versus storage or sequestration of carbon in soil. But we also have changing pools of carbon that are dominantly being affected at one point and another. But I think our work and work of several others have also shown that there is significant reaggregation and mineral stabilization of carbon that happens in depositional settings, which is why we have this really significant deposition-related sequestration of carbon in lower-lying depositional areas that are receiving carbon that is eroded from hill slopes. So in conclusion, I hope that I've convinced you that lateral redistribution of topsoil by soil erosion is a pretty important variable when we think about not just how much carbon is in soil, but where is it, and also its long-term fate. And also, I think our work and the work of several others have shown that this phenomenon of erosion-induced carbon sink is not restricted to natural erosion. It also seems to work with especially ag lands and grasslands, even ones that are highly disturbed. The only question that we still have open is whether this also plays out in forests. And that remains an open question. We're still not sure, and we're working on it to figure out if still would be a net sink even under forest ecosystems. My hunch is, even if it is, it's going to be a very, very tiny sink, simply because of the nature of carbon that's being eroded. But before I conclude, I want to make one important clarification here. I don't want anybody here to go away thinking that I am advocating that erosion is a management strategy for carbon sequestration. I know we probably won't, but I just want to be clear, right? This, as far as I'm concerned, and then the other folks that do this kind of work, is about trying to get a proper accounting of how and why carbon is stored and stabilized in soil, and how do geomorphic processes play a role. But we're not in any way thinking that this benefit of the small benefit of carbon sequestration that we get from erosion, as at least the Earth system gets, in any way compares to the effects of erosion, both for the loss of productivity, the soil health, and many, many other variables. Even if we were to take a very kind of centric viewpoint and say maybe there's a benefit economically, I don't think we still have any capacity to put it in the same kind of monetary terms to assess the potential versus loss in economy. So as far as I'm concerned, this is about figuring out how biogeochemistry interacts with geomorphology at the large scale to dictate how much carbon is taken out in the atmosphere or how much it stays in the atmosphere. But yeah, not a management strategy. Thank you. Yeah. Yes. Yeah, no, we do take, even without the supplements and fertilizer and irrigation, we take how NPP has changed. So the key point there to remember is that when you really think about how much carbon is actually lost by erosion at any given time, it's considerably smaller than the carbon coming into soil with NPP. Even if you go one step further and account for the humidification coefficient, meaning to figure out how much of that carbon coming with NPP is never really going to contribute to buildup of carbon and is quickly going to decompose, and just focus on that remaining pool that contributes to buildup of carbon pool. Several calculations and papers that we've published have shown that that pool that is coming in after erosion is more than enough to replace the carbon transported by erosion 4 up to sometimes 16 times over. So overall speaking, there's a lot more carbon coming into the soil, and the rate of erosion is also, at least under most conditions, is small enough that there's enough carbon coming in to replace plant productivity. Obviously, this means you can't have a soil where it's completely stripped, as I mentioned earlier. If it's bare and plant productivity is completely compromised, then we're talking about a different condition. Sometimes happens. Yeah, sometimes happens, right? And as a tribute to that, we have many places that stay bare. But relatively speaking, most erosion doesn't happen that way, right? So when you compare the net primary productivity in just downhill, and even if driving around on the freeway and you look at the mountains, the areas where it curves and soil accumulates, they always have higher plant productivity than the surrounding hill slopes, right? But part of it is because there's a lot of topsoil, fertile topsoil from hill slope that is being moved into these locations. Then the geomorphology or the shape of that landscape also encourages for water to stay there longer, and hence promotes higher rates of plant productivity. Calculations we've done with our own studies show that MPP rates are 2-3 times, if not more, higher in depositional settings of the same hill slope compared to even a vegetated eroding position upslope. So we've actually looked at landslide scars. So one of the dispositional settings that I showed you earlier, the hollow, one of the 2 depositional settings that was in the Tennessee Valley site, is actually a landslide scar that has been infilling for about 13,000 years or so. This one. That's why it's marked like that. It's a landslide scar that has been infilling for 13,000 years, and soil has been building up because of erosion and carbon then accumulating there. And actually, that is a pretty strong sink. So in some of the CZO sites that we're working on right now in forests, we see distinct higher rates of carbon that's moved in both the dissolvable pool and the total carbon overall when you have water, aquatic bodies, even streams right next to places that are steeply eroding hill slopes. So yeah, especially when it's being eroded from forests, you would expect that there would be tons of water extractable carbon that is entering, streams and then lakes and things like that. The point about groundwater is a little uncertain, right? Because in many ways, the soil profile acts as a chromatographic column to take carbon out of these dissolved phases and promote its association with soil minerals, right? So most of that carbon is stripped by the time it actually gets anywhere near groundwater. And this also happens to be the same thing when we think about surface versus subsurface flow of water. That if it's moved through the surface, you have a large pool of water extractable carbon that is entering aquatic bodies. But from subsurface flow or systems dominated by subsurface flow, like coarse soils that we have in the Sierras, it's not necessarily the case, especially if you have a lot of reactive minerals and it strips most of that carbon. We've seen this with naturally eroding soils. We've seen this with even fire-affected hill slopes where tons of carbon is being moved, but not through subsurface. So as soon as it encounters reactive minerals, it seems to be stripped, most of it at least. And so not a big pool seems to move that way. Yep.
So it sounds to me like you're saying they are just flat wrong. The source.
Pretty much. And unfortunately, it's a matter of this kind of perspective that I showed, right? We're really looking at this very differently. And in my opinion, if we are not looking at the role of erosion at a catchment scale, at least at the hill slope scale, we completely miss the picture of what's happening, right? So if you are focusing on that perspective, then yeah, erosion is going to be a source every time. But if you really consider what's happening down here and the fate of that carbon that's mobilized from hill slopes, I have a hard time thinking how you can arrive at a source. And we've been at this, unfortunately, this discussion for a while now. If you notice, some of these papers were published as I was starting my PhD. And so it's but there's been very many works at this point to verify from a mechanistic point, a global modeling perspective, and focusing on ag systems predominantly, focusing on lakes and reservoirs, or even taking a much bigger, broader global perspective. Everybody seems to be thinking this is a source. How big? We vary, right? The initial estimate that stirred a lot of the work that came afterwards was this synthesis work by Bob Stellard, where he worked through multiple simulations to think about the different types of distribution of depositional settings, different potential for carbon to decompose and be lost after erosion. And after this large modeling exercise, he comes up with the sink term. But the size of that sink could vary depending on what conditions you're considering. And I think he nicely captures all that variability that is in many of these works. And I'm only putting, a few of these works, but not just things that I've been associated with. Christophe Van Oust, for example, he's in Belgium. He's, probably has 30 papers at this point on this topic, pretty much all the time getting to a positive sink term, but not necessarily a huge sink term, but still a sink term. So from a mechanistic and all sorts of other perspectives, it makes sense that it has to be a sink term.
Any questions? All right, before we thank Asmeret, I'd like to acknowledge Larry Hips and Janice Bettinger for providing beverages tonight at King Home. So if you want to come down and enjoy those, and also Asmeret, if you haven't talked to anyone, she's got openings, I think, all the time for graduate students and postdocs looking for people to work with. So
Yes.
say hi. So let's thank Asmeret.
Thank you, guys. Thanks.